Okay, I think it started now. I hope you all can see my screen, and also those of you who are attending in YouTube can also see it. Thank you very much for attending. Welcome to one more lecture of our Processing in Memory course. Today we are going to continue talking about real-world processing in memory architectures. So in the last lecture, I was talking about the microarchitecture and I was talking about the microarchitecture and ISA of the first real-world processing in memory system, which is the UPMEM PIM architecture. Very briefly, to remind you, let's quickly refresh what we discussed, what we presented in the previous meeting. Recall that the UPMEM processing in memory system consists of multiple DDR4-like DIMMs that contain a number of chips, typically 8 or 16, and inside each of these chips we have memory arrays, DRAM banks, and small processors called DRAM processing units or DPUs. The system organization, as I said, an UPMEM DIMM typically contains 8 or 16 chips, and inside each PIM chip we have an MRAM bank. Well, we have 8 MRAM banks. The size of each of these MRAM banks is 64 megabytes. These MRAM banks are the DRAM arrays. And then we have, coupled to them, we have 8 DRAM processing units or DPUs. So in total, in one rank of 8 chips, we have 64 DPUs per rank. Inside the DRAM processing unit, inside the PIM chip, what we have is first, DDR4 interface for the host CPU to access the DRAM banks. Then we have a control status interface for the host CPU to communicate with the Dpu pipeline, send commands, and start the execution of kernels, for example, or be notified about the termination of a kernel. Then we can see here the 8 MRAM banks of 64 megabytes and 1 DMA engine per DPU connected via this 64-bit bus to the MRAM bank, and then 2 SRAM-based memory spaces, one for instructions and the other one for operands. And finally, the Dpu pipeline. We can take a closer look at the Dpu pipeline. Recall that this is an in-order pipeline. In the current architecture, it runs at a frequency of up to 350 megahertz. It's a fine-grained multi-threaded pipeline. It has 24 hardware threads. And essentially, we have here a dispatch unit that is fetching one instruction from a different hardware thread in each task, in each cycle, and issues it onto the pipeline. The pipeline has 14 stages: dispatch, fetch, read operand, format, ALU, and merge. And as you can see, according to this figure, different stages have different durations. So we can talk about 3, for example, 3 fetch stages, 3 read operand stages, 4 ALU stages, and so on. And we also talked briefly in the previous meeting about the Dpu Instruction Set Architecture. It's a 32-bit instruction set architecture, pretty rich with a large variety of instructions. Some of these we will see then when we talk about, I mean, in this lecture for sure, but also in later lectures when we talk about the DPU programming. Okay, so today what we are going to do is going over all the details of this microarchitecture. We are going to characterize these DRAM processing units, and we are going to explore what are the limits of these processing units, these DRAM processing units or these DPUs in terms of arithmetic throughput and in terms of memory bandwidth. There are 2 main memory spaces, as you know, for operands. One is the WRAM, which is SRAM based and is closer to the pipeline. It's a kind of a scratchpad memory, and then we have the larger one, which is the MRAM bank that we access using the DMA engine. So let's first start with the arithmetic throughput, and to measure the arithmetic throughput, we have created a micro benchmark where so our goal is to obtain what's the maximum arithmetic throughput for different data types and operations. In this micro benchmark, what we do is streaming over an array in WRAM. So we allocate an array of certain size in WRAM, and then we perform read, modify, write operations on all the elements of this array in WRAM. We run the experiments on one DPU. In the end, if you have a system with multiple DPUs, what you will obtain is the arithmetic throughput will be multiplied by the number of DPUs that you have in your system. So that's why we restrict this experiment to a single DPU. And we vary the number of tasklets from 1 to 24. Recall that a tasklet is one software thread running on the DPU. And because we have up to 24 hardware threads, then we change the number of tasklets from 1 to 24. Arithmetic operations that we are going to use in our experiments are addition, subtraction, multiplication, and division, and the data types are the ones that you see here: integer and floating point of single and double precision. Okay, so to perform the measurements, we use an accurate cycle counter that the UpMem SDK provides. And in our experiments, we include the accesses to WRAM, including the address calculation and the arithmetic operation. This is important because in reality, the amount of registers that we have per hardware thread is not that large. So it's not so frequent that we can store many intermediate results in the register. So it's very frequent that in like the common case, I would say, is that we have to go to WRAM to read and write operands as the computation makes progresses in our program. Okay, so let's start with the micro benchmark that we have used. And this is one of the cases for 32-bit integer values and the addition. You actually saw this code in the previous meeting because I use it for an example of what's the C-based code that we use in our programs and the compiled code using the UpMem Dpu ISA. So in the code, as you may recall, we have a for loop. In this for loop, we perform a number of iterations, essentially going over all the elements that has the array that we have allocated in WRAM using this memalloc instruction, which is a memory allocation in WRAM. And the for loop is that compiles to these instructions that you can see highlighted in yellow. So first we move 0 to the index, this I index, and then at the end of this loop, we have this addition to update the index and a conditional jump where we compare to the bound of this for loop. Here we have the access to WRAM. It's as simple as this array access in the C-based code. In the compiled code, we have first the address calculation. We need to obtain what's the address in WRAM, and then we load from WRAM. Here you have the addition. In the compiled code, we have the value that we read from WRAM is in R4, and R1 contains this scalar that we are adding to the temporal value. And finally, we store the result in the same position in this case, in this particular micro benchmark, as you can see this SW instruction here. So here are some results. And as you can see, we have 4 different plots. In the y-axis, we have the arithmetic throughput in mega operations per second. In the x-axis, we have the tasklets from 1 to 24, as you can see, and we have results for integer 32, integer 64, floating point, and double. These are the results for addition and subtraction. These are the results for multiplication and division. And these are the results for the rest of data types. And the first key observation here is that the arithmetic throughput of the DPU saturates at 11 tasklets. So this is consistent across data types and operations. And this is an important observation. And actually it relates to what we have. So it relates to the number of pipeline stages that we have in the pipeline. Recall that the number of pipeline stages is 14, but apparently the reason why the arithmetic throughput saturates at 11 and not 14 tasklets is because for a single tasklet, the dispatch unit can start issuing new instructions every 11 cycles. So it doesn't need to wait until the previous instruction has completely gone over the 14 stages of the pipeline. Okay, so one more observation is that there is a performance difference between the arithmetic throughput of integer 32 and integer 64 for addition and subtraction, where we are achieving the highest throughput, as you can see in these cases. So the integer 32 is essentially 17% faster than the integer 64 addition and subtraction. And we want to understand why this happens. And it's not that difficult to understand, as you will see. First of all, we are going to assume that we are working here after the saturation point with more than 11 tasklets. And when this happens, the pipeline is full. And when the pipeline is full, one instruction retires every cycle, one instruction from a different tasklet, of course. But in that case, we can assume that one instruction takes one cycle to execute, right? Because it's a fine-grained multi-threaded pipeline. So when we want to estimate what's the arithmetic throughput, we have to use this expression here, where in the numerator, we have the frequency of the DPU, and in the denominator, we have the number of instructions for the specific operation. So recall that here, we have our high-level code. This is the C code. This is for the micro benchmark for 32-bit operands, for integer operands. This is a micro benchmark for 64-bit integers. And here you have the compile code. This is a pretty useful tool called Compiler Explorer, and it's available for the AppMem system. And I would definitely recommend you to use it if you start programming the AppMem PIM system. One thing that we have to observe here is that for each of these accesses to WRAM and computations, these add operations that we have here, we need to execute a certain number of instructions. And these are, you already know these ones because we have shown them in the previous slide, but here we calculate the address in WRAM, here we load from WRAM, perform the addition, store to WRAM, and this is the index update and conditional jump. And this is the micro benchmark for 32 bits, right? For 32-bit integers. And now if we take a look at the micro benchmark for 64-bit integers, what we can see is that they both are essentially the same, and the only difference is this instruction here, this add C. So this add C is necessary because we are operating on 64-bit elements, right? And the pipeline is 32 bits. And our instructions are operate on 32-bit values in the end. So with this add C instruction, what we are doing is it's an addition plus carry, where we are adding the upper 32 of the 64 values, and we are also adding the carry that comes from the lower 32 bits of the 64 values. So that's why we have 7 instructions. In the case of 64-bit integers, we have 6 instructions in the case of 32-bit integers. And this is enough to explain this difference in performance, or this difference in arithmetic throughput between these two cases. So you know that we have we calculate the arithmetic throughput using this expression here. So if we take into account that for 32-bit integers, we need 6 instructions, and for 64-bit integers, we need 7 instructions, this results in 58.33 mega operations per second for integer 32 and 50 mega operations per second for integer 64. And this is essentially what we obtain in our measurements, as you can see in the plot. So this is what explains the performance difference here. We also see a large performance difference between, a large throughput difference between the addition and subtraction and the multiplication and division. And this is also something that we can explain. The reason is that DPUs don't have a 32-bit multiplier. They have an 8-bit multiplier, but not a 32-bit multiplier. And the reason for that is that it's pretty challenging to design a 32-bit multiplier, given the fact that we are working they are implementing the hardware with the DRAM technology, as actually we discussed in the previous meeting. So This is a reason. It doesn't mean that it's impossible to implement a 32-bit multiplier. It's simply that AppMem, for some reason, decided that it was better to prioritize other things, I assume. So the fact that we don't have a 32-bit multiplier means that we require an emulation implementation for multiplication and division. And this implementation emulates multiplication and division using instructions like actually one instruction that performs bit shifting and addition in one cycle. And what this means is that we are operating on 32-bit values, we may need up to 32 instructions, 32 cycles to execute the multiplication and division. And this will happen when we have like very long values, like occupying the whole 32 bits, because if you're using smaller values on 32 bits, the function itself that emulates multiplication and division will terminate earlier, right? So you will achieve some more, a little bit more higher throughput. In the case of our experiments, we used some random data. Okay, one more observation here is that there is a large performance difference between integer and floating point computations. And this happens not only for multiplication and division, but also for addition and subtraction. And the reason is that DPUs provide native hardware support for 32 and 64-bit integer addition and subtraction, as we have seen before, but they doesn't provide native support for multiplication and division, as we have discussed in the previous slide, but also not for floating point operations. So all of these are emulated, and this is what leads to the much lower throughput. Okay, so these are some of the results that you can later find in our paper as well. And the code is available for you if you want to use it, analyze, or rerun eventually. It's available in our benchmark suite, as you can see. Okay, guys, if you have any questions, feel free to stop me, or also post the questions in the chat. Yeah, so let's now discuss about, or let's now talk about the access to WRAM, right? So WRAM is accessed from the pipeline. It's a memory of size 64 kilobytes, and we are interested in measuring what's the bandwidth, at least the peak sustained bandwidth that the pipeline can obtain from WRAM. So to do that, we use a micro benchmark where we measure the WRAM bandwidth for the stream benchmark. To do so, we implement the 4 versions of a stream: copy, add, scale, and triad. And yeah, so just quickly remind you, because probably most of you or all of you are familiar with the stream benchmark. The operations that are performed in these 4 versions of a stream are, so there are no operations in copy because it's just copy. In add, we are using addition. In scale, we are using multiplication. And in triad, addition and multiplication. In our experiments, we vary the number of tasklets from 1 to 16, and we show result for 1 DPU. Observe that, or notice that in these experiments, we don't include the accesses to MRAM, right? Because we want to only focus on the WRAM bandwidth. Let's take a closer look at the stream benchmark. This is the copy stream benchmark. Again, same as we did in the previous micro benchmark, what we do is allocating an array in WRAM and then streaming over this array in WRAM. In the case of the copy stream benchmark, the only thing that we do is reading from buffer A, from one array in WRAM, and writing to another array in WRAM. So here we actually allocate 2 arrays, buffer A and buffer B in our example. Then we have add, where we have 3 arrays in WRAM, buffer A, B, and C. We read from A, we read from B, and we store the addition of these 2 into buffer C. Then we have a scale, as you can see, is reading from one input and multiplying by a scalar. And finally, in triad, we multiply by a scalar, and then we perform 1 addition. So by checking these codes, we can see that here in the first of the versions, we only read 8 bytes and we write 8 bytes because, by the way, we are using 64 integers in our experiment. So we read 8 bytes from WRAM, we write 8 bytes to WRAM, and there are no arithmetic operations. Here we read 16, we write 8, and there is one addition. Here we read 8, we write 8, and there is one multiplication. And here we read 16, we write 8, and there is one multiplication and one addition. These essentially are important and useful to understand the results that I'm going to show you in this next slide. So here you will see the plot for the 4 versions of stream in WRAM for integer, 64-bit integers on one DPU. On the y-axis, we see the sustained WRAM bandwidth, and here the number of tasklets changing from 1 to 16. So these are the results for copy, these are for add, and these are scale and triad. So let's start analyzing a little bit these results. So how can we estimate the bandwidth? Assuming that the pipeline is full, bytes is the number of bytes read and written, the number of bytes that we have seen in the previous slide, right? So we can estimate the bandwidth by using this expression. The bandwidth, the WRAM bandwidth in bytes per second is the number of bytes multiplied by the frequency of the DPU divided by the total number of instructions that we need in each of the cycles, in each of the iterations of the for loops. So for example, for copy, we execute 2 instructions. We only need one WRAM load and one WRAM store. If you really want to see the actual compiled code, you can use Compiler Explorer. You can just grab the code from a repository, go to Compiler Explorer, and confirm that only 2 instructions are used in each of the iterations of the for loop of the copy stream benchmark. So with when we have 11 tasklets or more, we would be reading 11 times 16 bytes in reading or writing 16 bytes in 22 cycles, right? Because we have 11 tasklets, 2 instructions, so in total 22 cycles. So by using these numbers here, we can obtain the WRAM bandwidth as 2,800 megabytes per second at 350 megahertz. And as you can see, this is very similar to what we are measuring in our experiments. So again, we can do the same for the addition stream benchmark. Here, in this case, we have 5 instructions. We have 2 loads. We have one ADC because we are operating on 64-bit integers, and we have one SD, one store to WRAM. With 11 tasklets, because we are reading from 2 arrays and writing to 1, we are reading in total, reading or writing 24 bytes, and we do this in 55 cycles. So this is our estimated WRAM bandwidth, which is also essentially the same as we are measuring in our experiments. And we can do similar calculations for the other 2 versions of stream. So key observation here is that the sustained bandwidth provided by the DPU's internal working memory or WRAM is independent of the memory access pattern. And this is something that we have confirmed by ourselves with some micro benchmark, which is also in our repository. In this micro benchmark, we do kind of indirect accesses to WRAM, and we have an array A that contains the indices that we want to access in other 2 arrays, A, B, and C, and we perform these accesses with different access patterns, right? So the first one is a unit stride, which is the same as a streaming access pattern because we go element by element. We also do this for a strided access where we change the stride, so we are kind of jumping a certain number of positions in the arrays B and C, and finally random access as well. So by using this micro benchmark, we confirm that the access to WRAM is independent of the memory access pattern, and also the second part of the observation is that all 8-byte WRAM loads and store take 1 cycle when the pipeline is full. And this makes perfect sense, right? Because these WRAM loads and stores are executed in the pipeline. And as you know, all instructions in the pipeline, all individual instructions from the ISA executed in the pipeline take 1 cycle when the pipeline is full. Okay, and here you have our micro benchmarks that you can find in the repository. So now let's take a look at the MRAM latency and bandwidth. So here what we put the focus is on this part of the PIM chip and this part of the DPU, where we have the 64 megabyte MRAM bank, we have the DMA engine, and on the other side, we have the 64 kilobyte WRAM. So to measure our goal is to measure the MRAM bandwidth for different access patterns, and to do so, we use different micro benchmarks. In the first one, we measured the latency of a single DMA transfer. There are two types of transfers, as you can guess. One is for reading from MRAM, which is copying from MRAM to WRAM, and the other one is for writing to MRAM. So it's copying from WRAM to MRAM. Then we also implement the 4 versions of the stream benchmark, and we actually have 2 versions of the copy benchmark. You will see in the next slide what's the difference between these two. We have also micro benchmarks for strided access patterns and one micro benchmark for the random access pattern. We essentially implemented the popular GAPS benchmark. And in this case, we include the accesses to MRAM because that's what we are measuring, right? The access to MRAM, latency and bandwidth. But let's start with the latency of a single DMA transfer. These are the plots where I'm going to show you the results. In the left y-axis, you see the bandwidth. Here you see the latency. This is for MRAM read. This is for MRAM write. And in the x-axis, what we have is the data transfer size. So when we execute this MRAM read and MRAM write, we have to indicate what's the number of bytes that we want to transfer in one direction or the other direction. And this number of bytes needs to be a multiple of 8 in this architecture. Okay, these are our measurements. The lighter blue is the latency, the darker blue is the bandwidth. The way that we obtain the bandwidth is by using this expression where size is the size of the data transfer, frequency divided by the measured MRAM latency. And one interesting observation is that we can model the MRAM latency with a linear expression. Actually, our linear expression looks something like this. It's a fixed term called alpha plus a variable term, which is, as you see, dependent on the size of the transfer, which is beta times size. And as you can see, our model, which is this thin black line, matches perfectly well our measurements. And according to our measurements and according to this linear model that we are using here, we obtain that beta equals 0.5 cycles per byte. So by using this number and taking into account what's the frequency of the DPU, we can obtain that the maximum theoretical MRAM bandwidth is 700 megabytes per second per DPU. So imagine when you have a system with thousands of DPUs, what's the overall bandwidth that you can achieve when accessing the MRAM banks. Okay, so key observation is that the MRAM bank access latency increases linearly with the transfer size. It's what we see with this simple model, and the maximum theoretical MRAM bandwidth is 2 bytes per cycle. Another observation is that read and write accesses to MRAM are symmetric. What this means is that these two plots look very, very similar, right? And the sustained MRAM bandwidth increases with the data transfer size. So one programming recommendation that we obtain from our observations is that as much as possible, we should use large DMA transfers. When all the data that we read is going to be accessed, we should make the transfers as large as possible, because this way we would be maximizing the bandwidth to MRAM. Another interesting observation here is that the latency changes very slowly between something like 8 and 128 bytes. And the reason for that is for small transfers, this variable cost is relatively small, right? Because size is not a large number, and this is only it's like 2 bytes per cycle, right? So, but this fixed cost is something larger. In our measurement, this is around 80 cycles. So for these small transfers, the fixed cost dominates. So that's why we don't see so much change in the latency for small transfers. So one programming recommendation from this is that wherever you need to access a number of bytes within 128 byte limit, it might make sense, it's worth it to bring even more data than what you really need in your program, because this will increase the possibility of finding the data in WRAM later. For sure, you will have to modify your program to be able to do so, right? And before issuing another request to MRAM to bring data from MRAM to WRAM, before doing that, your program has to check whether the desired data is in WRAM already or not. But that's actually kind of interesting programming optimization that you can try, and for sure will produce a nice performance improvement. Okay, one more observation is that 2048 byte transfers are only 4% faster than 1024 byte transfers. There is something interesting that we can also observe here, is that there is not much bandwidth difference. So there is really not much benefit from increasing the size of the transfers from 1024 to 2048. So in reality, it might not make sense to always fetch the larger amount of data. And why is that? Because every time that you want to transfer something between MRAM and WRAM, you need to have some space allocated for this chunk that we are transferring in WRAM, right? And the size of WRAM is not that large. It's only 64 kilobytes. And recall that we have up to 24 tasklets, up to 24 hardware threads. So we have to distribute these 64 kilobytes among all the tasklets that we are using, right? And what may happen if we allocate too much data in WRAM for each of the individual tasklets is that we are not able to use as many tasklets. So imagine that you need to use like 32 kilobytes per tasklet, and you only have 64 kilobytes, right? So what in WRAM? So what this means is that you can use at most 2 tasklets, right? So when bringing data from MRAM to WRAM, this is something to take into account. We don't want to reserve more WRAM than the necessary, because this is going to reduce the number of tasklets that we can use. And one way of reducing the amount of WRAM that we need for each of the individual tasklets is by using smaller transfers. Instead of moving 2048 bytes from MRAM to WRAM, we only move half of it, 1024, and this means that we are using half of the WRAM, and we can probably use more tasklets, which in the end is good to fill the pipeline completely and have this throughput of 1 instruction per cycle, as we have discussed in previous slides. Okay, now let's take a look at our next micro benchmark, which is the stream benchmark. As I said, we have 2 versions of copy, and let me show you what are the differences between these 2 versions. We have the version that we call copy, and in this version, what we have is this MRAM read. So we are reading something from MRAM to WRAM, and then we stream over this array in WRAM using this for loop, and this is exactly the same as the micro benchmark that we use for WRAM, and then we finally write the WRAM block back to MRAM, as you can see with this instruction here. So the difference with the copy DMA is that in copy DMA, we are just moving chunks between MRAM and WRAM back and forth, but we are not streaming over the WRAM arrays. As you can see here, we have 1 MRAM read and 1 MRAM write. So that's all. We are not really reading or writing from WRAM. So we in principle expect different bandwidth for these two different versions. Let's take a look at the results. So first of all, we are going to talk about the results for copy DMA, but here, as you can see, you see the sustained MRAM bandwidth. Here you see the number of tasklets from 1 to 16. Again, we are working on a single DPU. And the first observation for copy DMA, recall that copy DMA is just using the MRAM read and MRAM write. We are not reading or writing from the pipeline to WRAM. So what we can observe is that the sustained bandwidth of copy DMA is close to the theoretical bandwidth, the theoretical maximum bandwidth of 700 megabytes per second that we estimated previously. So this means that in the larger DPU system, in the larger UPMEM-based PIM system that we have using our experiments, we can achieve this impressive bandwidth. It's peak sustained bandwidth, which is even larger than in the most powerful GPUs these days. So one other observation here is that this microbenchmark saturates with only 2 tasklets, and this is interesting because in principle we were only expecting that with a single tasklet we were able to saturate the bandwidth, because the DMA engine is not exploiting memory level parallelism. It's just like issuing one transfer at a time. The thing is that when we are using 2 or more tasklets, we guarantee that there is always one DMA request in queue to keep the DMA engine busy all the time. So by doing so, we achieve a little bit higher bandwidth, as you can see in the plot. These are the results for copy and add versions of the stream benchmark, and what we observe is that they saturate at different number of tasklets, 4 and 6 respectively. And these are the results for triad and scale, and they both saturate at 11 tasklets. So this actually it's a very interesting discussion here. Why the copy and add don't saturate at 11 tasklets, which is what we could expect according to our previous measurements from the arithmetic throughput, where we have seen that for all data types and operations, the arithmetic throughput saturates at 11 tasklets. We don't observe that here because in reality, these two, copy and add, are very, very lightweight in computation, right? So in copy, the only thing that we are doing is reading one element from one array in WRAM and writing it to another array in WRAM, and then again reading and writing always in WRAM. In add, we are reading 2 values from WRAM, we are adding them and writing them to another place in WRAM, and after that we copy back the whole chunk to NRAM, as you know, right? But in reality, there is a very lightweight computation in these two. So what happens is that the latency of the NRAM accesses is longer than the latency in the pipeline for these 2 microbenchmarks. And this is what makes that in both cases, the bandwidth saturates with less than 11 tasklets. So the point where the latency of the NRAM accesses becomes longer than the pipeline latency is after 4 or 6 tasklets respectively. However, for scale and triad, the pipeline latency is always longer than the NRAM latency, and that's for any number of tasklets. And this is why the bandwidth saturates when the arithmetic throughput of the pipeline saturates, which is at 11 tasklets. But this is a kind of interesting observation, because this takes us to like this double observation here. It's like when the access latency to an NRAM bank is larger than the pipeline latency, the performance of the DPU saturates at a number of tasklets smaller than 11. And this is what we call a memory bound workload, memory bound in the UPMEM PIM architecture in the DPU. And when the pipeline latency is larger than the NRAM access latency, is the other way around. The performance saturates at 11 tasklets, and this is a compute bound workload in the UPMEM PIM architecture. Okay. I don't know if there are any questions from you guys, or maybe questions from people in YouTube. You feel free to paste them here in the chat if there is something interesting to discuss. Okay, yeah, so let's also take a look at the other experiments for strided access patterns and for random access patterns. In these, for these two, and actually for the strided access patterns, we have two different micro benchmarks. In the first one, we call it coarse grain strided access. The second one is called fine grain strided access, and I'm going to explain you the difference. In the first one, in the coarse grain strided access, what we do is reading two whole chunks. So here in this experiment, what we essentially do is reading from one array right into another array, and we do this in a strided manner, right? We are not accessing all elements in the arrays. We are just accessing with a certain stride, which is the distance between between two elements that are accessed by your program. So what we do is, because we want to copy from an array A in MRAM to an array B in MRAM, what we do is reading these two arrays in chunks, let's say chunks of 1024 bytes. That's what we are doing here. We read array A, so we read 1024 bytes from this array A, and we write them to buffer A in WRAM. We do the same for array B, and then we go over these two, buffer A and buffer B in WRAM, accessing with a certain stride. And after that, we have, let's say, the final results in this buffer B, and we write back the chunk from buffer B to the MRAM. This is in some way the same thing. It's kind of similar to what a CPU does when copying from an array A to an array B in the main memory. Instead of bringing whole chunks of 1024 bytes as we are doing in a CPU, what normally happens is that you read cache line by cache line, right? And but in some sense, it's similar. You're reading one cache line, you're putting them in your cache hierarchy, maybe in L1, and then copy from the cache line of array A to the cache line of array B, and at some point, this cache line will be evicted to the main memory. And then in our fine-grained strided access, which is also the same kind of program that let's say it's the same style of access that we use for random access as well. But the only thing that we are reading is the specific elements that we want to copy. So in this case, we are using one MRAM read. It's as short as 8 bytes, because we are reading elements of 64 bits. As you can see, so we have these MRAM read and MRAM write, and we are accessing these elements, these individual elements in MRAM with a certain stride, as you can see in the slide. So let's compare the bandwidth of these two approaches, the coarse grain strided and the fine grain strided and random approach. So these are the results for different strides. So on the y-axis, you see the sustained MRAM bandwidth. In the x-axis, you see the stride changing from 1 to 4096. In this case, one first thing that we can observe is that the bandwidth decreases pretty quickly when we increase the stride. However, in the coarse grain approach, however, in the fine grain approach, the bandwidth is completely flat. And let's see why. So first observation is that there is a large difference in the maximum sustained bandwidth between the coarse grain and the fine grain DMA. Why is that? The reason is that, okay, the maximum bandwidth for the coarse grain strided access happens when we are using a stride 1. And if you think about what's a stride 1 is essentially a stream access pattern, right? So what we are obtaining here, this maximum bandwidth is essentially the same as the maximum bandwidth that we obtain with a stream. But why is this so much larger than this one? The reason is that we are using different transfer sizes. The MRAM read and MRAM write transfers that we are using to move data between MRAM and WRAM are of different size. In the case of the coarse grain DMA, we are using transfers of 1024 bytes. In the case of the fine grain DMA approach, because we are reading individual elements, we are only using 8-byte transfers. And you can go back to the experiments where we measured the latency and the bandwidth for individual transfers, and you will see what's the large difference, bandwidth difference that exists between these two transfer sizes, and this clearly explains this difference from these 622 to these 72 megabytes per second. For random access, we obtain essentially the same bandwidth as for the fine-grained striated access, because we are using the same technique, let's say, or the same approach to access memory. Okay, one more observation is that the sustained bandwidth, the sustained MRAM bandwidth for the coarse-grained DMA approach decreases as the stride increases. The reason for that is that this is what we are representing here is that the effective bandwidth, right? It's not how much data we are reading from MRAM or writing to MRAM. It's not the total amount of data, it's the total amount of data that we are really using. And when we increase the stride, we reduce the number of elements in each of the chunks that we are really using, right? So, for example, a stride 4 means that only 1/4 of the transferred data is used. Recall that in the coarse-grained striated approach, we are using transfers of 1024 bytes. So what this means, stride 4 means, is that instead of using these 1024 bytes that we are moving back and forth, we are only effectively using 1/4 of that data. So that's what explains that the bandwidth decreases as we increase the stride. So another interesting observation is that when this goes down, what's the point where this bandwidth of the coarse-grained, or the effective bandwidth of the coarse-grained striated approach goes down, that is not worth anymore using the coarse-grained striated? Well, this happens when the stride is 16 or larger, as you can see. So this 77 corresponds to a stride of 8, because we are using 1/8 of the maximum bandwidth that we can achieve. And this is still slightly higher than the bandwidth that we can obtain with the fine-grained striated approach. But when it goes to the next one, is 16. So we are essentially dividing this by 2. So it's like 34 or so. No, it's like 37 or so. So this is much smaller than this, right? So whenever we are using a stride of 16 or larger, the fine-grained DMA approach achieves higher bandwidth and becomes a better choice for your program. So and essentially here what we have is the written explanation of what I just explained. At this point with the stride 16, only 1/16 of the maximum bandwidth is effectively used, and that's lower than these 72 megabytes per second. Okay, so programming recommendation number 4 is for strided access patterns that are with a small stride, something smaller than 16 8-byte elements. It's better to fetch a large contiguous chunk to use this coarse-grained approach. If not, you better use the fine-grained approach, where you only access from MRAM the values that you're really going to use in your program. And you can also check or micro benchmarks in the repository. Okay, now we are going to finish with something pretty interesting, I believe. This is the comparison between the arithmetic throughput and the operational intensity. So we want to see how the arithmetic throughput relates to the operational intensity of a program, because I believe that this is going to provide some interesting insights. So now we are kind of observing the behavior in all these different components, right? In the pipeline, we are going to perform some computation, but in order to do this computation, we first need to read from MRAM, write to WRAM, then perform some operations with on the data that is in WRAM, and then at some point when we have performed a certain number of operations on each individual elements of this WRAM, we write back to MRAM. So we create a micro benchmark where our goal here is to characterize the memory bound regions and compute bound regions for different data types and operations. And in our micro benchmark, as I said, we read from MRAM to WRAM, then we perform a variable number of operations on the data that we have in WRAM, and then we write back to MRAM. Essentially, this variable number of operations on the data is the operational intensity. The operational intensity is higher when we perform more additions or more multiplications on each of the individual elements that we have in WRAM. This experiment is inspired by the popular roofline model. As you may know, the roofline model represents the performance of a system with respect to the operational or arithmetic intensity. In our case, we define the operational intensity as the number of arithmetic operations performed per byte accessed from MRAM. And you have to take into account that for each of the individual operations that we are executing, so each addition or each multiplication, we need to read from WRAM, we need to operate on the pipeline, perform or use the ALUs in the pipeline, and then write back to WRAM, right? And also these are the let's say the instructions in the pipeline that determine the pipeline latency. And as you can see, the pipeline latency is going to be dependent on the operational intensity, because higher operational intensity means more instructions executed in the pipeline, but the MRAM access latency is fixed. And why is that? Because we are bringing one chunk from MRAM to WRAM, then computing a variable number of operations on this, and then writing back the chunk, but the size of the chunk is always the same, right? So that's why the MRAM access latency is fixed. Okay, and actually, this is the code of the micro benchmark. This is where we read this chunk. Here we have a like two nested for loops to like control what's the number of operations that we perform on each of the individual elements that we have in WRAM. In this case, it's the addition, and here it's the final write back operation with this MRAM write. In our code, we have like two, let's say, parameters, repetitions and stride, but they both depend on the this input repeat, which represents in some way the operational intensity. An input repeat greater or equal to 1 indicates that the number of repetitions indicates the number of repetitions per element. So, for example, if this input repeat is 2, means that on this buffer AI we are going to perform 2 additions, or if it's 4, it will be 4 additions or 4 subtractions or multiplications. If this input repeat is smaller than 1, this indicates the fraction of elements that are updated. So for example, if this input repeat is 0.5, it means that we are not updating all elements in buffer A. We are only updating 1 element every 2, and we only perform 1 addition on that element. So that's how this micro benchmark works. And by using this micro benchmark, we obtain these results. So here you see the arithmetic throughput, and here you see the operational intensity. You can notice that we are using like from very, very low operational intensity values. This is only 1 arithmetic operation per 2048 bytes, right? So it's very, very low to something relatively high, right? Like 8 operations per byte. And we have results here for integer 32 addition and multiplication, and floating point addition and multiplication. We are going to discuss a few trends that we observe here. These trends are consistent across data types and operations. The only thing that is going to change is the maximum throughput that you can achieve, and also these saturation points, or the point where the shape of the curve changes, as you can see. But that's so the actual numbers here are not so important. The trends are more important and more interesting, and they are pretty similar in all cases. So let's first take a look at we are actually going to focus on the integer 32-bit integer addition on one DPU. Recall, here we have the arithmetic throughput, and here we have the operational intensity. And one thing I want you to see is that this plot is composed by many of these dots, and there is a number inside the dot, and this represents the number of tasklets that we are using for different operational intensities and for different, of course, data types and operations. So these are the results for one single tasklet for this operational intensity. These are the results for 2 tasklets. And as you can see, for higher number of tasklets, the arithmetic throughput does not change. So we can say that for this low operational intensity, the throughput saturates at only 2 tasklets. And we see that this is more or less the trend as we increase the operational intensity until this point, 1/64, right? And here you see that this is 1/32. And here we see that the saturation happens at 3 tasklets. And then the maximum, the arithmetic throughput remains constant for higher number of tasklets. And we see that for higher operational intensity, the saturation point, it's for higher number of tasklets, but at some point it saturates. And then for 1/4, we see that the saturation point actually happens at 11 tasklets. And what this means is that now we are saturating the pipeline. And at this point is when the latency of the pipeline becomes longer than the latency of the MRAM accesses. So this is why we define a memory bound region and a compute bound region. So the memory bound region is this region where the arithmetic throughput increases with the operational intensity. The compute bound region is this area here where the arithmetic throughput is flat at its maximum. And we call the throughput saturation point, this point here, 1/4 in this particular experiment, where the transition between the memory bound region and the compute bound region happens. And this throughput saturation point, as you can see, is pretty low, is only 1/4. 1/4 here means 1 integer addition per every 32-bit element fetched from memory. So it's a relatively low, and it's even lower, as you can see in the plot, for other data types and operations. So one key observation is that the arithmetic throughput of the DPU saturates at low or very low operational intensity. And what this means is that a DPU is fundamentally a compute-bound processor. So the arithmetic throughput saturates at very low operational intensity. So it's very likely that one real-world workload is going to overwhelm the pipeline, and so we and execute as many instructions in the pipeline that the latency of the accesses to MRAM is completely hidden, right? And this is kind of a interesting and surprising observation as well, especially if we compare to other real-world systems like CPUs or GPUs, where in most of the programs we are saturated by the access to memory. And here, what happens is exactly the other way around. So that's why we say that this is a compute-bound processor. So from this, what we expect is that most real-world workloads will be compute-bound in the PIM architecture. So even something that might be highly memory-bound in a CPU or a GPU, we expect that will be compute bound in the PIM architecture. And we are also, I mean, we will talk in later lectures about real world workloads on this PIM architecture, and you will see that this is actually what happens, that most real world workloads are in the compute bound area of the roofline, and and the performance saturates at 11 tasklets. Okay, and yeah, you can also find the code in our repository. So in summary, and actually I'm finishing the lecture for today. The most important takeaway from this lecture is that there is a memory bound region, there is a compute bound region, and the throughput saturation point is pretty low for all data types and operations. These are, for example, the results for addition of 32-bit integer values. Key takeaway is that the PIM architecture is fundamentally a compute-bound architecture, and as a result, the most suitable workloads are those workloads that are memory-bound in conventional processor-centric systems, and we expect that these will be compute-bound in the PIM architecture. But this is something that we will keep discussing, and we will see results for real-world workloads in later lectures. But if you are impatient, you can directly go to our paper and read it, or you can watch the whole talk that I gave some time ago. And these are some contents that we will continue covering in later lectures. So I hope that you are enjoying this series of lectures. Yeah, we hope that they are useful to many people. And at this point, I only want to thank for your attention and also ask if there are any additional questions from our students or from YouTube. If not, I think that we are done for today with the lecture part of our meeting. Okay, we are done. Thank you very much. See you next